Assalamualaikum and hi everyone. So this is a video on how to design a PI controller for DC motors. So basically this is the overall block diagram for this system.
36 volt is set as input DC voltage, 3.2 ohm and 4.66 millihenry is set as the armature resistance and inductance. This is the transfer function of the system where it is 1/Js plus B. J value is 45.9 microkilogram meter squared and B is 0.00001 kilogram meter squared per second. This scan is set to 60/2 pi to change the output value from radian per second into RPM. The first and the third input for the speed control is 2150 RPM, while the second input is set to 4300 RPM. Then the gain is set to 2 pi over 60 to change the RPM input value into radian per second. These are the values for proportional gain and integral gain for speed control loop. The saturation upper limit and lower limit are set to 3 and -3 to ensure that the controller output stays within the defined range. These are the proportional gain and integral gain for the top control loop. The repeating sequence value is 1/20 kHz, where the 20 kHz is the switching frequency of the system. It is set based on a triangular waveform which is 2.529 volt because it provides a linear and predictable modulation pattern for pulse width modulation. After all the parameters has been set, we can run the simulation.
So this is the output graph from the simulation. Based on the graph, the motor operates with positive voltage and positive current in the first quadrant, where the load is driven in forward direction. The torque and the speed are both positive. Thus, the power is positive too. During this quadrant, the motor is operating as forward motoring. During this phase, the motor converts electrical energy to mechanical energy to produce a positive torque. Hence, the direction of torque is anti-clockwise during this phase. The rise in the voltage and current shows that the motor is accelerating in forward direction, which indicates the motoring function of the motor. In the second quadrant, the motor is operating as forward braking. During this condition, the current is negative while the voltage remains positive. Therefore, the torque is negative while the speed remains positive. So, the power of the motor is currently negative. The motor converts the mechanical energy to electrical energy, which means that the motor is acting as a generator. The regenerative braking operation of the motor allows the motor to slow down and restoring back the energy to the power source.
Quadrant 3 involves the DC motor operating in reverse braking. The graph shows the segment where both the current and voltage are negative during this condition. The torque and the speed are negative as well, hence causing the direction of torque to be clockwise and the power is positive. During reverse motoring, the motor converts the electrical energy to mechanical energy, driving the load backward effectively. Lastly, in the fourth quadrant, the motor is operating in reverse braking. The graph shows that the current is positive while the voltage is negative. So, the torque is positive while the speed is negative, causing the direction of torque to become anti-clockwise and the power is negative. The motor converts the mechanical energy back to electrical energy, indicating that the motor acts as a generator, similar to in quadrant 2. The 4-quadrant operation confirms that the capability of the permanent magnet DC motor in delivering satisfactory performance in motoring and braking modes both in forward and reverse direction. The ripple in the graph can be related to the proportional gain Kp and integral gain Ki parameters of the PI controller used in the control system. As the value of Kp increases, the system becomes more sensitive to change. This can result in faster response but with the drawback of overshooting and oscillating, and which can contribute to ripple. Similarly, with the increase in the Ki value, the impact of the accumulated error is also increased, thus having a better ability to counter steady-state errors. However, it can also lead to higher oscillations and ripple as the system continuously adjusts the past errors.
That's all from us. Thank you guys.